This is a tutorial on mathematical induction. Mathematical induction is just a method to prove a mathematical statement is true. Like this mathematical statement here, the sum of k, where k ranges from 1 to a maximum value n, is always equal to n times n plus 1 over 2. Now here is my sequence k. And because this sequence is being summed, you can call it a series, but this would be our first term, our second, our third, our fourth, and so on. Then if we want the sum of all these terms, then we should be able to use this formula. But if we don't know that this formula is true, or we want to prove that this formula is true, well, we could check every value of n. So let's check it for the first value of n, or our first term, 1. So if n is equal to 1, and I plug that into this formula here, of 1 times 1 plus 1 over 2. Now 1 plus 1 is 2, 2 times 1 is 2, so this is 2 over 2, and that's equal to 1. Well, our first term is 1, and if we sum it to, well, it's the only term, so the sum would be equal to 1. So that works. Now let's try our next value of n. Well, our next value of n would be 2, because n is just the number of terms in this series or sequence. So if we plug in 2 for n, we get 2 times 2 plus 1 over 2. 2 plus 1 is 3. 3 times 2 is 6. So this is 6 over 2, which is equal to 3. And if I take my first two terms of my series, 2 and 1, and I add them together, well, I get 3. So it works for those two terms. Now let's try our third one. And then we can try our fourth one, and the fifth one, and the sixth one, all the way up to, well, this goes to infinity. Well, that's a lot of values of n to plug into this formula to make sure it works for each one of them. So instead of plugging in every value of n possible to verify this formula, instead, let's use mathematical induction. When we use mathematical induction, our formula must fit two different conditions. The first condition we check is that the formula must work for the first natural number, when k is equal to 1, or you can think of when n is equal to 1. The formula must work for the first term in our sequence. If it works for the first term in our sequence and condition 1 is met, we move on to condition 2, and we say that the statement is valid for all values of k. So if we assume that it's valid for all values of k, all we have to do is check if it's valid for the next natural number, k plus 1. So if we go back to our formula, and we say that this formula should work for all values of k, or all values of n, then we just check and see if it works for the next value, k plus 1. Because k can be any one of these values. And if we say it works for any one of these single values, then we just check and see if it works for the next value, because then it means it works for all the values. Think of this as some dominoes stood up in a line. If you pushed over one domino and it knocks over the next one, well then it must knock over the next one and the one after that, and the one after that, and the one after that. So let's see how this works. We want to prove that this statement, the sum of k when k ranges from 1 to n, is equal to n times n plus 1 over 2. So we want to say that this works for all values of k, or for any term in our series. So our sequence, or our summation of a sequence, looks like 1 plus 2 plus 3, and this goes up all the way up to some maximum value k, which is just where we stop. And this has to be equal to k times k plus 1 over 2. All I did was take k, which is the spot that we're going to check in our sequence, and plug it in for n. So now that we have this statement, we need to check this for the first value of k, or our first term when k is equal to 1. So our sequence would look like 1, and that would be equal to 1, which going in for k, times 1 plus 1 over 2. Now 1 plus 1 is 2, 2 times 1 is 2, this is 2 over 2, and that's equal to 1. So our summation of our sequence is equal to 1, and our formula is equal to 1, which means it works for the first value of k, or our first term. So condition 1 is met. Now we have to check our second condition. And when we do that, we say that this statement here is true, which is a generic statement for any value of k or any spot in this sequence. If we say that this is true for any generic spot in this sequence, we next want to test and see if it's true for the next spot in our sequence, or the k plus 1 spot. So our sequence is going to look like 1 plus 2 plus 3 plus all the way up to k, and then to the next term, k plus 1. And this should be equal to, now everywhere I had a k before, I'm going to put a k plus 1. K plus 1 times k plus 1 plus 1 over 2. Now again, we're just testing this for the next value in our sequence. Now the way to check this is you have to remember that we assume that this statement, since 1 worked, this statement is true for all values of k. Well, if you look what I have right here, this is the left-hand side of this equation. So I can substitute all of this in for k times k plus 1 over 2, because this is equal to 1 plus 2 plus 3 all the way up to k. We still have a k plus 1 on the outside, and this is still equal to k plus 1 over k. Now plus 1 would be k plus 2 over 2. So now that I've done this substitution, my objective is to prove that these two sides of this equation are equal. To do this, I'm going to multiply this term here by 2 over 2, just so I have a common denominator. So this will become k times k plus 1 plus 2 times k plus 1 all over 2, and it's still equal to k plus 1 over k plus 2 over 2. Now I'm going to simplify this numerator. K times k is k squared. K times 1 is plus k. If I distribute the 2 inside, I'll have 2k plus 2. So this is k squared plus 3k plus 2. And I can factor that into k plus 2 times k plus 1. But remember, this is just my numerator, so this is all over 2. And this is exactly the same as this. So my two sides of my equation are equal. And that means that condition 2 is met. And if we meet both of these conditions, that means that this equation here is true. So now let's look at another example. Here we have a series, and this is equal to n times n minus 4. So I want to check this for all values of k. So my formula would look like 3 minus 1 plus 3 plus 11 plus all the numbers all the way up to 2 to the k power minus 5. And this is supposedly equal to k times k minus 4. So the first thing I do for condition 1 is check that this works for the value k is equal to 1. Well, if k is equal to 1, all we have is our first term. So we'll have negative 3 has to be equal to 1 times 1 minus 4. Our first term has to be equal to our formula when k is equal to 1. Now 1 minus 4 is a negative 3. Negative 3 times 1 is still negative 3, so this is negative 3 is equal to negative 3, and that is correct. So condition 1 is satisfied. Now we assume that this equation must be true because it works for k is equal to 1. So now we have to check the equation where we have negative 3 minus 1 plus 3 plus 11 plus all the numbers all the way up to 2k minus 5, and then the number after that, which is 2 to the k plus 1 minus 5. And this is supposedly equal to k plus 1, which goes in for k, times k plus 1 minus 4. Now we're going to do the same substitution we did before. Remember this minus 3 minus 1 plus 3 plus 11 all the way up to 2k minus 5. This is all equal to k times k minus 4, because we assume that this equation works. So we have k times k minus 4 plus 2 to the k plus 1 power minus 5 is equal to k plus 1 times k plus 1 minus 4 would be minus 3. Now if we simplify this, this is k squared minus 4k minus 5 plus 2 times 2 to the k. I split up this exponent as 2 to the first power times 2k. And this is equal to k squared minus 2k minus 3. If we subtract k squared from both sides, those will cancel. If I add 4k to both sides, that will cancel and this will become positive. And if I add 5 to both sides, that will go away and this will become positive 2. So I have 2 times 2 to the k power is equal to 2k plus 2. Divide everything by 2 and I'll have 2 to the k is equal to k plus 1. This is as far as I can simplify this. This does work for our first value of k, but every other value of k, this will not work. 2 to the k power is not equal to k plus 1. I could not get these two sides of the equation to be the same, which means this thing fails condition 2, which means that this is not a valid equation for every value of n. Now typically we use mathematical induction to compare two equations, or you can think of two different sequences. Here we're saying 3 to the n power is always greater than 2 to the n plus 1 power. Now if we wanted to check this, we could check it for any value of n, and the random value of n that we're going to choose is k. So that means that 3 to the k must be greater than 2 to the k plus 1. Now the first thing we do is check this equation for a k value of 1. 3 to the 1 must be greater than 2 to the 1 plus 1 power. Well, 3 to the 1 is 3, and 2 to the 1 plus 1 power is 4. 3 is not greater than 4, which means this fails condition 1, which means we don't even have to do condition 2. This is not true, or it's never true for every value of n. So let's see what happens when we change our equation around a little bit. Here we have 3 to the n is greater than 2 to the n. We lost our plus 1 here. We want to see if this is true for all values of n. So we pick a random value of n, which we call k. So 3 to the k has to be greater than 2 to the k. And if this is true, then it has to be true for our first value of k when k is equal to 1. So 3 to the 1 must be greater than 2 to the 1, which is 3 must be greater than 2. That makes sense. So we satisfy condition 1. Now we have to check condition 2. That assumes that it works for the next value after k. So 3 to the k plus 1 must be greater than 2 to the k plus 1. Now when we have this greater than or less than sign and we're comparing it this way as an inequality, oftentimes it's easier to go back to our original equation, which, remember, we're assuming that this is true. If I multiply both sides of this equation by 3, I'll have 3 times 3 to the k, and that must be greater than 3 times 2 to the k power. Well, 3 times 3 to the k power is the same as 3 to the k plus 1 power. This is still greater than 3 times 2 to the k. Now I have a 3 to the k plus 1 power here, and it's greater than 3 times 2 to the k power. Now this equation came from this equation, which we assume is true, which means we can always assume that this equation is true. Now if we go back to this k plus 1 equation here, where 3 to the k plus 1 is greater than 2 to the k plus 1, looking at this right-hand side, I can think of this as 2 to the k times 2 to the first power. I'm just breaking up this exponent, which means 3 to the k plus 1 has to be greater than 2 times 2 to the k. Well, I know from this statement here that this is true. 3 to the k plus 1 I know is greater than 3 times 2 to the k power. This is the statement that I know is true. I can also look at these two. Remember, k comes from our natural numbers. K is always a positive integer. Well, 3 times 2 to the k power has to be greater than 2 times 2 to the k power. If I divide both sides of this by 2 to the k power, they'll cancel and 3 is greater than 2. So I know that this has to be greater than this. If I know that this statement is true, and I know that this statement is true, that means this one has to be greater than this one. So 3 to the k plus 1 must be greater than 2 times 2 to the k plus 1, which is just a rewrite of this formula here. So since we proved that this formula is true, that means that this equation satisfies condition 2. That means that this is true for all values of n. So now let's look at one more example. Here we want to use mathematical induction to prove that every term in the sequence an is equal to 2 to the n is divisible by 2. Now we want to make sure that this works for all values of n, so we select a value of n at random. And again, we call that value k. So a, when n is equal to k, is equal to 2 to the k power. Now we want to check for when k is equal to 1. So we plug in 1 for k, which means our first term is equal to 2 to the first power, or our first term is equal to 2. This term is divisible by 2. So we meet condition 1. Now we want to check and see that, assuming that this statement is always true, that the statement a to the k plus 1 is equal to 2 to the k plus 1 is always true. So we want to be able to prove that 2 to the k plus 1 is always divisible by 2. Well, I can rewrite this as 2 to the k times 2 to the first power. All I'm doing is separating my exponents. Now we already said that this is divisible by 2. So if I multiply it by 2, well, 2 is also divisible by 2. So if I divide this by 2, I just go back to my original 2 to the k power. So that means that 2 to the k plus 1 is also divisible by 2. And that meets condition 2. So this is true for all values of n. So that's how you use mathematical induction to check to see if certain mathematical expressions are valid. And that completes the tutorial on mathematical induction.